Alright, cool. So in the previous video, we did the best of the best classifiers, right? And in this video, we said we are going to discuss now. We're going to get into LDA. We're going to get into LDA. So in this first part, we're going to say LDA for P equal to 1. So for one predictor, we're going to use one predictor. That is the easiest. That's what we usually do, right? We did simple linear regression, and then we moved to multiple linear regression. We did just simple logistic regression, then we moved to multiple logistic regression. That's the same thing we're going to do here. We're going to do, let's just call it simple LDA, because we have one predictor, and then later we're going to look at what about LDA that has multiple predictors. So for LDA that is predictor equal to 1, we would like to estimate, like we discussed, we would like to estimate our f of kx, right? That we can plug into that equation that we had and get an estimate of the probabilities. Then we are home and dry. We are home and dry, right? So let's discuss how we calculate this f of x. Let's make two assumptions about f of x, about this fkx assumptions. Let's make these assumptions. First assumption, we're going to assume that fkx is normal or Gaussian. So it's from a normal or Gaussian distribution, right? It's normally or it's normally, that is the easiest way to say it. It's normally distributed. These these probabilities here. You remember these densities. Let's assume that our densities in all classes, they are normally distributed. They are normally distributed, right? That's what we're saying. They are normally distributed like that. Cool. Let's assume they are normally distributed. That at the bottom here we have a few, and then we have a maximum here in the middle, and then tapping off like that with some symmetry here, with a symmetry there. They are normally distributed. Cool. And if they are normally distributed in a one-dimensional setting like we have right now, in a one-dimensional setting like we have, normal distribution means our fkx takes this form: 1 over 2 pi the standard deviation of that class multiplied by the exponent. Also, this is e to the power of standard deviation of the class, which is the variance. So this becomes the variance x minus the mean of that class. So this is going to be squared. Yeah, that is equal to squared, right? So that is just if they are normally distributed. If they are normally distributed, right? It means the density for our x is going to be given by this. It's going to be given by this. That's what it means, right? When they are normally distributed. Nasty looking formula. Yeah, it's nasty. I wouldn't lie. But it comes from statistics. In the bonus videos, we can discuss this formula here. But for our uses right now, we will just take them as gospel, right? So this one here, this is going to be equal to the mean. It is the mean for the kth class. For the kth class. So this is mean of the kth class, and this delta squared is going to be equal to the variance. It is the variance of kth class. Variance of the kth class. Cool. So second assumption, we are going to assume the variance for the first class is equal to the variance of the second class is equal to the variance of the kth class, right? So here we're saying we have something called a shared variance. We have a shared variance. Across k classes, across the k classes. We have a shared variance. So with our second assumption, let's put these two into our formula for P. If you remembered from the previous video, it was saying our pkx is equal to pi k, and here that's where our f of xk was, right? F of fkx was, so we're going to write this fkx, that nasty part there, 1 over square root of 2 pi delta. So yeah, I'm just going to say delta and not delta k, because we said we have assumed a shared variance, so we're just going to call that shared variance equal to just this delta. So it's good, delta squared. Let's call it delta squared. So instead of delta k, we're just going to write our delta. So it's going to be delta there, the shared variance, shared standard deviation. It's not standard deviation because it's not squared, right? 1 over 2 variance, shared variance, x minus mu k squared, like that. Cool. All divided by our summation there. Our summation says L equal to 1 to k, and then we are going to have my pi L, and what are we having now? 1 over square root of 2 pi, this, the shared standard deviation, exponent of 1 divided by this x minus this. Cool. It's just fitting this f of x into the formula that we had from the previous video. Cool. That is going to be our pkx, right? Pkx, right? So now let's see. Let me confirm from my notes how I'm going to, because I want to see if that is important. Oh yeah, something happened. Okay, so it opened something that I didn't want to open. Cool. So I think that part you agree with, right? With our two assumptions, you agree with that part. So now what we are going to do now, in normal life, in real life, we would have had, or no, not in real life, in simulated data, we can easily get this f of k. We'll be like, oh yeah, coming from a normal distribution, you're doing the whatever it is, normal distribution, we can have all these parameters because it's simulated data. It is simulated data, right? But in normal situations, we do not have these parameters. We don't have these parameters because it's just data that is there in real life. We do not have the mean, we do not have the variance and stuff. We don't have maybe shared variances and all of that, all complications, right? So since we want to have all those parameters like the pi k, we can calculate, but some things like the mu of k and the what do you call this, and the shared variance, it might be difficult to calculate. So LDA will try to approximate that. How it's going to do it? So the linear discriminant analysis method approximates the Bayes classifier by plugging in estimates of this. So let me use a different color. So LDA now will come and say, okay, dude, this is your Bayes classifier. That is your Bayes classifier. But that is for someone who's fortunate enough to know the true values of these parameters here. It will say, yeah, oh, you have a shared variance. Ah, okay. And you know what it is? Cool. You know what the shared variance is? Cool. Huh? You see? And the pi. So the Bayes classifier, the Bayes classifier like that. But then LDA will come and say, dude, in real life, when you're doing real data science, when you have real data, more often than not, you're not going to know those parameters. And LDA is going to try and estimate these parameters here. LDA is going to try and estimate your pi. It's going to try and estimate this variance. And it's going to try and estimate this mu. Because when it estimates that, it's going to come up with an estimate for f of k. And when it comes up with an estimate for f of k, it's going to put it into, remember the formula from the previous one, for the Bayes one. right? And if it does a good job at estimating these green parameters here, these parameters that have been circled, if it does a good job of estimating these parameters here, it might be very close to the ultimate, the best of the best, the Bayes classifier. So basically that is what LDA does. It tries to estimate those parameters, because when it estimates those parameters, it puts it into that formula. Remember that formula that pi k fk over summation with the pi l and then the flx. You remember that formula? It's going to put in, because this formula is going to give us our it's going to give us our probability estimate. It's going to give us our probability estimate, right? So this part here is going to try and estimate those. It's going to try and estimate those. So how is it going to do that? Let's see. Let me delete everything and we can just see how LDA does that. Right? So with that nasty formula, right? What we can do with that nasty formula is, okay, it looks very nasty when it's written in that way, right? What we can you remember, it was written like, okay, let me write. You remember that pKa that we had, that pKx formula that we had, which had the pi k 1 over. Please bear with me as I rewrite it here, because I'm going to reference it. 1 minus 2 x minus mu k squared. This is going to be equal to, divided by the summation of L equal to 1 up to k pi of L 1 over square root of 2 pi exponent, or 1 minus squared x minus mu L, so this k mu L, like that. So cool. This looks very nasty, right? And it has exponents and stuff like that. As a challenge to yourself, try rewrite this formula, getting rid of the exponent using logarithms, right? When you do that, you are going to come up with, I'm going to create a new symbol. You're going to come up with this. They're going to come up with an equation that's like this. This can be in the bonus videos if you want to see the derivation here. You're going to come up with an equation that is like this. Minus squared k over 2 delta squared plus log of pi k. That is the formula that you are going to come up with, right? That's the formula that you're going to come up with when you rewrite that, trying to clean this up better. You're going to come up with this formula here. And when you come up with that formula there, what this then means, LDA is going to come back and say, I'm going to help you estimate this. That is what LDA does, right? That's what we want LDA to help us do. Because this is still coming from Bayes, because those are the true values. And LDA is going to be like, nah, don't worry. I'm going to help you estimate those, right? I'm going to help you estimate those. How does it do it? This is what we are discussing now. How does it do it? Cool. The estimates that it uses are, you remember from normal statistics, how do you get a mean of, let's say a mean of a sample? A mean of a sample is going to be equal to what? It's going to be equal to how many things are in that class divided by what do you call this? Okay, yeah, let me say it's going to be, if it's a sample and you want to know the mean of the sample, you just add everything up. Divided by what? Divided by how many things there are in that class, right? That's exactly how LDA is going to do it. It's going to say 1 divided by nk, the number of observations in class K, sum, and then you sum. So this is just notation. This is just notation. Don't worry about the notation. Xi. So this is the mean of all observations in training class K. In training class K. Training class K. So that is the mean of all observations in training class K. Right? We are dealing with class K. So what is the mean there? We just add we add everything up, and we divide by the number of observations in what? In that class K. And the variance is going to be a bit nasty. This is the formula for the shared variance. The shared variance is going to be given by K equal to 1 all the way up to the last. So this part is saying for each class we're going to sum up all the classes. But what are we summing up from all the classes? It means in each class we are going to do something like this. We are going to just calculate xi minus this. So basically in each class we sum up the difference between each observation minus the mean, right? That is in each class. We are going to sum those up. And we are going to do that for all other classes, for every other class. So in each class we do the summation. And then we sum up over all classes. And then we just do n minus k. So the number of observations minus the number of classes. So this is something called I think it is a weighted. I think it's a weighted variance. I will have to confirm this. I think it's called a weighted variance or something like that, right? I think it's called a weighted variance. So that is our estimate. So yeah, this is actually called the weighted average of sample variances. Weighted average of sample variances for each of the K classes. We've just weighted them, and then we can apply it to everything for each one of them. Cool, right? So those are the estimate that our LDA will calculate, and they have heads here showing them as what? As estimates. It's showing them nicely as estimates. And that makes sense, right? So we have this estimate and we have this estimate now. What about this pi k? Pi k is the easiest to calculate. The estimate for pi k. It is just equal to the number in the kth class divided by the total number of observations in our training class. In our training data. So if our class is females, right? If our class is females, k equal to female, then it's just going to be number of females divided by how many people we had in our training data. Easy. Now we have this one here. So now we have all our estimates from LDA. We now have all our estimates in LDA, right? When we have our estimates in LDA, we then just plug them into the equation, that equation that we had, and LDA assigns, and then what LDA, if we plug them into the equation, we can plug them into the original equation. It's just going to be our pi k, f of k, calculate our f of k and stuff like that, and then we're going to have our probability and stuff like that. Or we can be clever, because this f of x was basically this part here. When we rewrote this section here, it was this, right? You remember, it was this side, this part here. You remember when we substituted our f of k with this section here from 1 over square root with this section here. So we can substitute our estimates into this one here if we want to calculate this probability like that, right? Or we can be clever, because this we basically rewrote this and we created a new variable called delta, this delta k, and it's just a parameter. But what parameter is that? We can use that parameter now because we are going to do this for all classes. We are going to have this parameter value for all classes, right? Imagine we had 10 classes. We are going to have delta 1, delta 2, delta 3, delta 4, calculating using our estimates for each class that we have. LDA has helped us calculate. LDA has helped us calculate this for class number 1, we get our delta. For class number 2, we get our delta using these estimates here. See these estimates for each class here. Cool. For class number 3, class number 4, all the way up to class number 10. And we will be smart because we rewrote this instead of choosing the class that has the biggest probability, because we want to assign this observation to the originally we would say the class that has the biggest probability, but because we rewrote the probability and created this parameter delta, we are going to assign observation to class with maximum delta, maximum delta, whatever that delta is going to be. The class with the maximum delta, when we calculate it this way for each class with our estimates like this, whatever it's going to be, with our whatever that when we keep the deltas, delta 1, delta 2, delta 3, and we compare these deltas now. Which delta has the highest delta? Oh, it's class number 4, which means this observation is going to be put into class number 4. It is an easier way than going through the probabilities. This is much easier. It's much easier. It's much easier, right? It's much easier. This applies when what? You remember our assumptions. Our assumptions was the f of k's and stuff like that. The densities are coming from a normal distribution with a common variance and stuff like that. If we have large data sets, and usually you get something like that. You get something that is what do you call this? A large data set. That is those kind of variances, right? So let's see. Let me look at my notes here. This has been a very long video. Let's see if my notes, if I can squeeze in a video here, or I would have to do it in another. I think I'll do it in the next video. But so far, that's what we discussed. We discussed that our LDA tries to mimic the Bayes classifier, because the Bayes is the best of the best. So our LDA will try to mimic that. But we'll try to mimic that, because in real life we do not have these values here. We do not have these parameters here. So it will try to estimate those parameters using these estimates here, And when we're using those estimates, we then just choose. We give the observation to the class that is the maximum delta. That maximum delta. And that's it. That is what LDA does. And this is easy because it was based on P equal to 1. One observation. In the next video, we're going to move on to LDA that is more prediction. So more predictors. And this is going to be sort of like our multiple linear regression or our multiple logistic regression. And we're going to see how is LDA going to handle such a situation. It's also going to be technical, but I hope these basics for the one where P equal to 1 makes sense. But it's going to be enjoyable. So we will meet in the next video.